All right, welcome students. Today we are going to shift things a little bit. We were looking at graphs of equations, and now we're going to be looking at solving systems of equations by graphing. Let me first give you the definition of a system of equations. A system of equations is a set of two or more equations with two or more variables to be solved simultaneously. In this class, we're going to focus on systems of equations with two equations and two variables, generally, though in future classes, you might see systems with three equations and three variables, or four equations and four variables. Now, when this says to be solved simultaneously, that doesn't mean we've got a pencil in one hand and a pencil in the other hand, and in one hand we're solving one equation and the other hand we're solving the other equation. That's not what we mean here. When we say to be solved simultaneously, that just means that whatever solution we find has to work in all of the equations. It has to make all of them true, that one solution. So what I want to do is I want to look at an example and figure out how we can solve our first system of equations. So let's look at our first example. Let's solve 3x plus 2y equals 18 and y equals 2x minus 5. This is a system of equations with two equations that have two variables, x and y. Now, we haven't seen a system of equations before, but we have looked at equations like these already. And there's one thing that we know we can do with equations like these. We can sketch their graphs. Each one of these is going to have a graph that's going to end up being a line. So each one of these is going to end up being a line. And remember, that line represents all of the solutions to that equation. So one line is going to represent all of the solutions to one equation. The other line is going to represent all of the solutions to that other equation. And because we're looking for a solution that works in both of the equations, we're looking for a point on both of the lines. And so what we're really looking for is that intersection point. So we're going to want to graph both of these on the same plane and figure out where they intersect. Let's go ahead and do it. All right, I want to start off with 3x plus 2y equals 18. Now we have three choices for how we can graph this. We can make a table of values. We can find the x and y intercepts. I call that the intercept method. Or we can use slope-intercept form. Now, I want to use multiple methods for these different examples because I want us to get practice using all of them. And so for this one, I'm going to use the intercept method because when x and y are on the same side, oftentimes the intercept method is the easiest to use. So to find the x-intercept, what we need to do is we need to let y equal 0. If we do that, this becomes 3x plus 2 times 0 equals 18. We know that anything times 0 is 0, so that goes away, and we're just left with 3x equals 18. Now, if we divide both sides by 3, 18 divided by 3 is 6, so we get x equals 6, and that's the x-intercept. We can even plot that now. We find 6 on the x-axis, and there we go. Now, to find the y-intercept, what we need to do is we need to let x equal 0. If we do that, we've got 3 times 0 plus 2y equals 18. We know anything times 0 is 0, so that term's going to go away, leaving us with just 2y equals 18. To get y alone, we need to divide both sides by 2, and when we do that, that gives us y equals 9. So we can plot that. The only issue is, if we look at our y-axis, we've got 5, 6, 7, 8. 8 is the highest number, but we can go up one more unit to give us our 9, and then we can connect the dots to get our line. So this is the line 3x plus 2y equals 18. All right, let's take a look at the other one. Now, the other one, y equals 2x minus 5. Let's rewrite that down here. Y equals 2x minus 5. We could use the intercept method here. However, there's an easier method. Slope-intercept method is going to be simpler here because this is already in slope-intercept form. In this case, the slope is the coefficient on the x, which is 2, and the y-intercept is the constant term, which is -5. We can use this to sketch the graph without doing any actual calculations. The y-intercept is our starting point, and that's at -5, so we can start down there. The slope is 2. Now, we usually like to view the slope as a fraction so that we can see it as rise over run. We can make 2 a fraction by putting it over 1. So that means we're going to rise up 2 and run to the right 1 from our starting point. So we go up 2 and to the right 1, and that gives us another point. And we can keep going. Up 2 and to the right 1 gives us another point. Up 2 and to the right 1 gives us another point. And we can keep going. Up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. And we can connect the dots. And then this is the graph of the equation y equals 2x minus 5. All right. So this first graph represents all of the points that are solutions to 3x plus 2y equals 18. This second graph represents all the points that are solutions to y equals 2x minus 5. But we're solving this system of equations. We want a point that's a solution to both of them at the same time. And there's only one point that's on both of those lines, and that is our solution point. It has coordinates 4, 3, but really the nicest way to write this out is to include the variables. So x equals 4 and y equals 3 is our solution. The reason I don't want to just leave it in coordinate form is because later we're going to be seeing systems of equations where the variables aren't x and y. Maybe they're m and n, or c and f, who knows? And so in that case, it makes a lot more sense to say the first variable is 4, the second variable is 3, to actually write it out like that. Now, with these problems, it's imperative that you're drawing accurate graphs. If you're being sloppy with your lines and they're not drawn nicely, it's going to be much harder to see where they intersect. So I strongly recommend that you use graph paper and you use a ruler or some other straight edge to draw nice, beautiful lines so it's easy for you to see your solution in the end. Take a look at some of the other worked out examples to get some more practice. And then next class, we're going to see some interesting situations where it's not always so clear what's going on.